In this section, we will talk about list. List is a polymorphic variant type, which is also self-recursive and immutable. What does it all mean? You will find out shortly. If you are not sure how recursion works in Reason, take a look at one of the previous sections where we talked about recursion in detail. In the previous section, we talked about parameterized types in Reason. And the list is a parameterized type as well. It's an essential data structure of functional programming. And that's why there is a predefined parameterized type for a list in Reason. Let's take a look at it. This is an illustration of how the list variant type is defined in Reason. It's somehow different from other variants we've seen so far. As you can see, it's referring to itself in its own definition. So we are reusing the name of the type we are defining. This means that a list is a self-recursive variant type. And because of that, it doesn't have a flat structure, like other data structures we've already talked about, such as tuples, records, and arrays. This means we will be able to define deep data structures using a list type. It has two constructors, empty list and the first element of the current list and the rest, which points to another list with the remaining elements. We are using the spread operator inside the second constructor. We will talk more about the spread operator later. We can also think about a list type like this. The first element of the current list is called head, and the rest is called tail. And since list is a variant type, we can process it using pattern matching. This is just another illustration. In pattern matching, we want to cover all the possible cases of the variant type to eliminate possible bugs. Since the list has two constructors, we need to cover these two. So we first check if the list is empty, and if it's not, we can use the first element of the list, called head, and the rest, called tail, for some computations. We've mentioned that a list is a parameterized type. In a simplified way, we can think of a list like this. List, as a parameterized type, is expecting a type variable alpha as an argument, which can be any type. This means we can pass a type variable to the list as an argument, which will determine the final type, which can be, for example, a list of strings, a list of integers, and so on. This means that elements of a list can have any type, and it also means they must all have the same type. For better understanding, it's useful to think about a list as of a type function expecting any type. When we pass a particular type, we will get back the concrete type that we can use in our computations. Let's take a look at some examples. We defined the identifier integer list, and the compiler inferred that it's a predefined list with an integer type variable as an argument. So the resulting type is a list of integers. We also defined another identifier, string list, and the compiler inferred that it's again predefined list type, but this time with a string type variable as an argument. So the resulting type is a list of strings. As you can see, we have a single list variant type which can be used to create a list with any elements. And this is the power of the parameterized types. Without them, we would need to manually define a type for every list with a different type, such as list of strings, list of integers, list of floats, and so on. With parameterized types, we only need a single reusable list type. And since the list variant is predefined, we don't need to declare a type for list in advance as we do with other variants. You might also notice that we are defining our list the same way we've seen in the illustrations. We write the first element called head, in this case it's 1, followed by another list called tail, and then another head, and another tail, and so on. At the end we have an empty list. If we take a look at our illustration now, it's the same logic. We have the first element head, and then the rest called tail, which points to another list. And finally, we have an empty list at the end. So you can see both constructors of a list type in our example. Let's take a look at how the compiler inferred our type. As you can see, it's telling us that integer list is a list of integers, and the string list is a list of strings. Moreover, it's suggesting us to use more compact syntax, as you can see here and here. So our code is equivalent to this. As you can see, we can also define a list by enumerating its elements, which is convenient since it makes our code much more readable when you compare this syntax to this syntax. However, it's still important to understand the original syntax for lists in order to properly use them in our computations. Lists are syntactically similar to arrays. The difference is we use only square brackets to encapsulate lists elements. Since we know how to create a list, we can now process it using pattern matching. Let's use it to compute the length of a list. We defined the getLength recursive function, which computes the length of a list. When defining a recursive function, we need to use a rec keyword. It allows us to refer to the function which we are currently defining. Our function expects a list as an argument and performs pattern matching over this list using a switch. Finally, it returns the length of a list, which is an integer. Since a list is a parameterized variant type, we can use this function to get the length of a list containing any type. So our getLength function is polymorphic. Let's verify this by calling our function with different arguments. We passed a list of integers, strings, and floats to our function, and we got back the length of each list. Let's take the first example and describe how this function works. Here we pass a list of integers as random list to the getLength function. We take the random list and perform pattern matching. We are matching two constructors of a list variant type. Since our list is not empty, we skip the first case, so we go to the second case. Here, we take the first element of the list, but we are not using it. We also take the rest of the list, tail, which now contains remaining 3 integers, and then we add 1 to the length of the list which is being computed, and call the function recursively with a shorter version of the list using tail. Each time we do a recursive call, tail will become shorter. We will do these recursive calls until the tail is empty. Then we will get back 0 and compute and return the length of the list. As you can see, we are using an underscore in the pattern instead of the first element of the list. And we are doing this since we don't need this value for our computations, because we just need to count the elements in the list. And we are using an underscore to tell this to the compiler. Otherwise, we would get a warning. The getLength function is pretty reusable. We used it to get the length of the list of integers, strings, and floats. And we don't need to define a new version of this function for each list type. And this is possible because list is a parameterized type. Since getting the length of a list is a common operation, this function is predefined in the list module, which is a part of the standard library. And this function is called list.length. Let's use this predefined function instead of our custom one. As you can see, it works the same way. The standard library contains many other predefined functions for dealing with lists. And these functions are all polymorphic, meaning they don't depend on the type of the elements. This means they are created once and can be used for all lists containing any types. Let's take a look at more ways of creating a list. Here we have a list of two elements called characters, and we want it to prepend three other elements before it. We achieve that using the spread operator. We created a new list, this right here, and passed three elements there, Luke, Leah, and Han. Then we used the spread operator to expand the characters list. This expansion means that each and every element in the characters list is inserted into this new list. In our example, we inserted Obi-Wan and Yoda elements into the new list. So we can use the spread operator to prepend 0 or more elements before an existing list. The spread operator is similar to the JavaScript spreads operator. However, in Reason, it's more limited since we can use it only at the end of a list. Let's take a look. We tried to concatenate two lists using the spread operator at two places, here and here, and we got an error. Fortunately, Reason has also a special operator for these kinds of situations. We defined two lists, and we used add operator to concatenate them together, and we got back a new list. The add operator is Reason's concatenation operator. However, concatenating lists using this operator is slower than using the spread operator. It's because the add operator goes through every element in the first list and adds it into the second list. So, in our example, it doesn't complete in 2 moves, but in 3 moves. We first moved Luke to the second list, then we moved Leia, and finally Han. The more efficient way to concatenate two lists is to use a recursive function. We defined the append function, which expects two lists, list 1 and list 2, and performs pattern matching on list 1. Our pattern matching covers 2 cases of a list variant type. The first case is matched if the list 1 is empty, and the second one if it's not empty. Let's call our function to see how it works. We pass 2 lists to the append function. We take the list 1, which contains 3 elements, and perform pattern matching. Since our list is not empty, we skip the first case, so we go to the second case. We extract the first element of the list 1, which is Luke, and add it as the first element of our new concatenated list. Then we pass the tail, which now contains 2 elements, and list 2 to the append function and call it recursively. And during each recursive call, another element from list 1 will be added to the new concatenated list. First it will be Leia, and then Han. And we will do these recursive calls until list 1 will be an empty list. Then we will match the first case and get back list 2, which will be added at the end of our new concatenated list. And you can see the resulting list here.